We have two matrices here which are 2 by 3 in nature. So you have 2 by 3, 2 by 3. Nevertheless, the goal here is to solve for the kernel and nullity of their linear transformation. The kernel is actually the set of all vectors that could make this 0. Okay? 0 in what way? Since we have here matrices, we have here the transformation using a certain vector v is equal to a times your certain vector v, which would be equal to the 0 vector. Okay? Now the 0 vector here is actually dependent on the type of linear transformation here. Take note, we have a 2 by 3 matrices here. If we have here m by n, okay, m by n, the transformation here is from Rn to R to the m. In short, we have here R3 to R2. That would mean that our vector that we're going to solve here, vector v, is an element of our domain, which is in R3 in nature. So our 0 vector here is R2 in nature, so that this would be defined. This same thing goes as the other example. So the purpose of this is just to illustrate the form of the 0 vector and the vector v to which we're going to come up with the values for the components to come up with our kernel. In short, our v here, since it's an element of R3, can be in this form: v sub 1, v sub 2, and v sub 3. So we are going to solve for the components for v sub 1, v sub 2, and v sub 3. That would again be equal this one here to our 0 vector in R2, which is 0 and 0. Why are this very important? Again, so that our linear transformation using matrix is defined. But before we start with that, the technique here is to come up with the row echelon form of this. You can use reduced row echelon form. It's okay with that. I'm just going to use here a certain row echelon form, okay, to make this even shorter. But then again, if you're going to proceed with reduced row echelon form, it's still okay. It's even what they call this one, more even exact, and you don't need additional steps. But here, let me just have the row echelon form: 1, -1, 2, 0, 1, and then 2 here. Okay, so let's try to, this is already 1 and 1. By the way, this is already in row echelon form, right? Because we have leading 1, okay, and no other zeros there. So just for this, okay, let us make this in reduced row echelon form. In short, making this 0. What we could do here is to add row 2 plus row 1 for a new row 1, just to include a step here. So this would become 0, this would become 4, okay? This would become 1, and this is 2 when you add row 2 and row 1 for the new row 1. With this, since this is already in the reduced row echelon form, let's multiply this with our vector v. Again, it's on R3 because of this. So we have here v sub 1, v sub 2, v sub 3 equal to our 0 vector in R2, 0 and 0. Of course, you could also verify whether your analysis is correct, because once you multiply this is defined. Because if you just end up with 2 components, this is not defined. The product is not defined. So the form here, we have v sub 1 plus 0 v sub 2 plus 4 v sub 3 is equal to 0. The second is v sub 2 plus 2 v sub 3 is equal to 0. We still have 2 unknowns per equations, so we can let here v sub 3 be an arbitrary constant t. Okay? With that, this second equation, in solving for v sub 2, you'll have, that's plus 2t equal to 0, where v sub 3 is t. So v sub 2 is equal to negative 2t. And then for our first equation, v sub 1 plus 4t equal to 0. That's our v sub 3. So v sub 1 is negative 4t. That would mean our vector, okay, vector here has components of v sub 1 is negative 4t, v sub 2 is negative 2t, and v sub t is t. In the form of, we can of course factor out t that in that manner, right? So we will have our kernel now. Kernel, or yeah, the kernel of t is a set containing all vectors. So we are going to factor out t. You have -4, -2, and 1, such that t is an element of R. This is now your kernel. Okay? The kernel is the set of all vectors in this form. So meaning there are many, but there's only one specific vector here, and pertaining to your nullity, because nullity of t talks about the dimension of the basis of your kernel. We only have one here, so the nullity of t is just equal to 1. Okay, so we have 1, and this is the kernel of t. Let's duplicate the same process on our second example here. Again, same concern, same process here. Reduce row echelon form. 1, -2, 1, 0, 2, and 1. To make this 0, we will be adding row 2 and row 1 for a new row 1. This would mean that we have this 1, 0, this would become 0, 2, and this would become 2 and 1. Okay? For a 1, this is not 1. So let's try to come up with the process. Let me redo it. My bad. We are going to make this 1 first. So 1/2 of row 2 for our new row 2. 1, -2, 1, 0. This becomes 1. This is 1/2. Okay? Now, we can now multiply 2 to row 2 plus row 1 to make this 0, because our goal is a reduced row echelon form. We have 1, 0. Of course, this is still 1. 2 times 1 is 2 plus -2, 0. 2 times 1/2 is 1 plus 1, so 2. We have here 1/2. This is now the reduced row echelon form, so multiply now your vector, and this is equal to, again, our 0 vector in R2. So with these spaces here, let me divide here. So our first equation is v sub 1 plus 2 v sub 3 is 0. We have v sub 2 plus 1/2 of v sub 3 be 0. Same. Let v sub 3, just for the purpose of the discussion, since we already used t earlier, let me use here s. Either way, it's an arbitrary constant. In this case, this will become v sub 2 plus 1/2 s equals 0. V sub 2 is -1/2 of s. This equation here, v sub 1 plus 2s equals 0. V sub 1 is -2s. With all these 3, our vector now here, we'll have the components, v sub 1 -2s, v sub 2 -1/2 s, and v sub 3 being s. Or, again, you could factor out s there, but let's just proceed immediately to the kernel of t. With a set of all vectors with s as our scalar here. -2, -1/2, and then 1 as you factor out s, such that s is an element of R. Okay? This is our kernel, and the nullity, okay, there's of t is equal to 1, as this is only a vector here as the basis of the kernel. So same here, 1, we have this kernel for the second matrix here. So this is how we solve the kernel and nullity of a linear transformation involving 2 by 3 matrices. Thank you for watching.